a recording. And I'd like to welcome everyone to the October Joint Atmosphere and Arctic Observing Systems IARPC team meeting. So really excited today to have a set of lightning talks about technological advancements in atmospheric observing science. As some background, my name is Andrew. I'm a member of the IARPC Secretariat. A few housekeeping notes. Please keep yourselves on mute during the presentations. We are recording this meeting. The recording will be uploaded on the IARPC webpage later this week. As a secondary note, we also have our code of conduct that we've updated this year. I'm going to put it in the chat. Encourage everyone to please be respectful of everyone here today. And so we're thrilled. So Hazel, who's also a member of the Secretariat, will be note-taking for us today. What I would like everyone to do is just in the chat, go ahead and put your name and affiliation. And if it's your first time to an IARPC meeting, this just helps us get a head count of who attended today. And once we have done that, I will pass the baton over to Sally, who will introduce today's meeting topic.
Great, thank you, Andrew. Hello, everyone. Thank you for joining the meeting today. I'm not sure I see a lot of familiar faces, but there might be a few people who are new to IARPC. The acronym stands for the Interagency Arctic Research Policy Committee, and IARPC brings together staff from 16 different agencies, departments, and offices across the US federal government to enhance research in the Arctic. And the IARPC collaboration teams are a method or a platform to connect the federal researchers with non-federal researchers, the academic community, and other stakeholders to inform each other and work together on Arctic research. So today's meeting is co-sponsored by two of those collaboration teams, the Atmosphere Collaboration Team and the Arctic Observing System Team. So my name is Sally McFarlane, and I'm a program manager at the US Department of Energy, and I'm a co-lead for the Observing System Team. And my other two co-leads, both of whom are on the call today, are Will Ambrose at Coastal Carolina University and Sandy Starkweather at NOAA and University of Colorado. And then our co-host for the meeting is the Atmosphere team, and they are co-led by Barry Leffer at NASA. I don't see Barry on the call, and Colleen Hafke at NSF, and also Heist DeBoer from NOAA and University of Colorado Boulder. And I want to particularly acknowledge Heist, who actually put most of the work into organizing this meeting, but then he actually ended up being out in the field this week, so he wasn't able to join. So as Andrew mentioned at the beginning, this meeting is focused on observing technologies deployed in support of Arctic atmospheric science. So that's why we brought these two teams together on this topic. Our meeting's gonna start with an overview of by Mark Seefeldt on the polar technology community. And that's gonna include details on current trends and considerations in the deployment of new technologies in polar environments. And then we're going to have a series of 2-minute lightning presentations that are going to provide information on actually quite a broad range of observing technologies that are deployed to or over the Arctic environment. So we're looking forward to hearing from those speakers. After the lightning presentations, we have a little bit of time for discussion and questions for the presenters, and then any updates from the attendees. I encourage you, we will have a little time at the end, as I mentioned, for discussion, but I also encourage you, if you have questions during the presentations, to put them in the chat. So with that, I think we can go ahead and get started, and we'll start with Mark.
Okay, first, just want to make sure everyone can see the PowerPoint. Okay.
Yep.
Okay, great. Mark, take it away.
All right, good afternoon, everybody. Thanks for coming for this session. And I'm here to talk about the polar technology community And with that will come an understanding of the history of where we got to polar technology community, as well as some of the recent meeting we had in 2020 and ideas that we have going forward. Next slide. All right, so the Polar Technology Conference was initiated out of informal gatherings at Stanford University in the early 2000s. The initial gatherings were involving small autonomous power stations, power systems, weather stations, communication systems for the polar environment. The early meetings going back to 2005 with formal meetings were held at SRI International in Menlo Park, California. And then it started an annual tradition of having the Polar Technology Conference at 9 different locations across the United States, where this meeting of engineers, technicians, field personnel would come together to discuss things that they had learned in the field, problems that they were having in the field, and getting together ideas and experiences to further the application of technology. These early years, we relied on volunteers and participating organizations to host the meetings, as well as to put the program together. In 2017, the meeting was delayed and then went on a hiatus due to a lack of funding source, as well as a planning team. Basically, the meeting had grown to the point of needing a dedicated funding source. Next slide. NSF OPP then provided funding starting in 2018 to look at restarting the PTC, and they tasked ARCIS to provide the administrative and to host and organize the event. The goal was to, along the lines of the old original PTCs, to link the polar science and technology development, and to bring in partners from industry, academia, government, and military together to share their experiences. It was a range of disciplines that came together, looking at terrestrial, marine, atmospheric, social sciences, and all levels of logistical support. The meeting was held in Boulder to have it in a central location, easily accessible by a large number of people. And you'll see that it was held 10 to 12 March 2020. And that might ring a bell because we were literally having the meeting as the country was shutting down due to COVID. There were some people that were not able to make it because of COVID travel restrictions, especially the international community. There were people that had to cancel 3 days ahead of time because their organization shut down travel. And basically, we just barely squeaked in this conference. The original scope was to have 100 in-person attendees. And then we had 29 cancellations along the way. And the online presentation format that was set up by ARCIS long before COVID hit ended up being a significant boost for the ability for people to attend remotely that were not able to due to last minute travel restrictions. Next slide. The conference was focused on 6 themes, and this was areas of common needs of industry, needs and interest across discipline. The 6 themes are science drivers, power systems, communications, data access and sharing, then overarching and integrative technologies. In this slide, I've highlighted the middle 4 because these are 4 that are applicable to a wide range of field deployments, no matter the science. These are things that everybody has to consider and to have common goals and be able to understand and perfect these areas in the polar environment. Next slide. We also included some novel ways in which we can get together and share ideas and brainstorm. And one of them was on the first day, we had a breakout session of groups of 8 to 10, where there was a peer coaching approach taken. All of the participants were given an opportunity to share a polar technology challenge in their own work. Then they would receive guidance from the people at their table and problem-solving suggestions from the collective group and how they may address or solve the issue that they were dealing with. This received a lot of positive support as it allowed people to sort of get at ground level ideas and thinkings and not just listening to presentations. We also included a special session on satellite communication with high interest in this area, with the emphasis on sort of that communications and data transfer. Next slide. The return of the PTC was met by enthusiasm by the community. People were excited that we were able to get together and come up with sort of that back going into the just hanging out and sharing ideas and experiences. In looking at future meetings, brainstormed ideas, topics that came up was things such as having a discussion on half-baked ideas. A participant throws out ideas to be incubated and discussed among the groups for just sort of like brainstorming and just coming up with positives and negatives on how something may be approached. There's ideas of having incorporated training sessions with the PTC, such as Polar Geospatial Center providing a half-day tutorial to provide information and hands-on services provided by the PTC. Future meetings are expected to occur every 2 years, typically in March or September, which is our transition between the Arctic and the field seasons, and a central location to make easy access for the larger community. We're also hoping to have increased participation in future years. This is again impacted significantly by COVID impacts. Next slide. As we grew away or went away from the PTC 2020, we decided to rebrand Polar Technology Conference to instead call it Polar Technology Community. And behind this is the concept of being able to have it a year-round, bringing together people, sharing experiences and ideas. And we like the PTC acronym, but we wanted to make it sort of a year-round participation. So we went with Polar Technology Community as the rebranding. Next slide. Within this, then, we created a self-forming team on IARPIC to promote the sharing of information for the community. And so if you're interested in this, you can go to the IARPIC website and search Polar Technology Community Forum and join that forum for future announcements and updates on the Polar Technology community. Next slide. As is mentioned, the workshops are expected to be held every 2 years, funding contingent. There was a zap of momentum from the PTC due to COVID, in that we sort of everybody got tied up into all of the happenings that we had by being shut down, that there's not been any discussion on the next PTC, and it sort of just got delayed due to COVID and all that. So there's been no talk exactly of when the next PTC workshop will be, and that will probably need to be initiated by funding organization. We've talked about having PTC webinars every quarter. However, the deluge of Zoom meetings and conferences from the past year and a half tempered that enthusiasm a little bit. And also talking about having a forum that brings people together. So you can think of it as like a stack exchange for Polar Technology, where people are able to propose ideas or questions that they may have, then get feedback from the community. Next slide. So looking at lessons learned, we were able to see that there is still strong interest in pooling the ideas and experiences in applying technology in the polar regions, focusing on common areas that allows it to be shared across disciplines, as well as then partnering with industry at all levels to really make a direct connection into advancements in technology and research and development technology from an industry perspective to be provided into the field. And so next slide. So the funding provided by NSF OPP. If you're interested in the Polar Technology Conference, ARCIS still has the website with the agenda, and all of the recordings up are posted, that you can still view all of the presentations from PTC 2020. And again, you can go to IARPIC to join the Polar Technology Community Forum. And feel free also to reach out with me for any questions that you might have involving the Polar Technology community. And that's it.
Great, thank you, Mark. It's very interesting. I want to note that the IARPIC, for those of you not familiar with IARPIC, they have IARPIC has a 5-year research plan, and we're currently in the process of drafting and finalizing the updated plan. And technology is going to be what we're calling a foundational activity in that plan. So I think the self-forming team and connecting technology to that new plan is really timely and will be great. We had hoped to have a brief presentation on that aspect of the plan, but since the plan is expected to be finalized and released in December, I think we're going to wait to have that discussion. Andrew, do we have time for a quick question, or do we need to move on?
I think we should hold some of the questions until we're all set with the rapid questions.
Okay, so we'll move on to our lightning presentations. I will note there's a question in the chat, and Mark's welcome to reply to that in the chat if you'd like to. Our first lightning presentation will be by Naruki Hiranuma from West Texas A&M, and he's going to talk about ice nucleation.
All right, thank you, Sari. My name is Naruki Hiranuma. My team is doing ice nucleating particle INP research across the world. So if you can see the map on the bottom, since 2017, my team has been in 2 Arctic stations, including Spitsbergen and Battle, Alaska, and the 2 stations in the mid-latitude. So now let's talk about INP. INP represents a small, tiny population of particles in the atmosphere. Approximately 1 in a million aerosol particles act as INP, okay, at some temperatures in the clouds. But it has a great and a giant impact on Arctic climate warming, according to the recent study done by Ben Murray et al., a very good friend of mine and a good collaborator of mine. Basically, long story short, what he's saying is, like, if we have more INPs, there will be more of the Arctic warming for many reasons, right? I'm not gonna, tell all the details, but my point is studying, like, ice nucleating particles is very important in atmospheric science community. And mainly that is because INP define the balance between ice and water in the Arctic clouds, basically impacting climate, okay? But it's sad that the latest IPCC report says that the climate models basically ignore INPs, which is resulting in the notorious plus minus 100% uncertainties in the projection of aerosol climate interactions, okay? Now, to fill this gap, my team has reviewed INP studies all the way from 1959. And we have implemented a new technology in collaboration with German researchers to take more measurements of the INPs for the next few years in the Arctic station in Battle, Alaska. We have implemented a remotely controlled pine chamber, portable ice nucleation experiment chamber at the NOAA BRW stations since like last Wednesday. And we're going to be monitoring INP abundance here for the next 2-3 years. What's great about Pine Chamber is that we can measure INP every 15 minutes or so. With the technologies used previously, it took minimum a few hours to measure INPs, but now we slim it down to 10 to 15 minutes. So I expect this good time resolution can bring more science and more meaningful data to improve the uncertainty in the climate models in the future. And I have been collaborating with this
wrap it up.
All right, modelers,
Yes,
and
yeah,
thank you so much. I think that's it.
Sorry for that short 2 minutes. Does go by quickly.
That's
Great.
good.
Thank you, Naruki.
Thank you.
And all of the, I think the slides are going to be available on the IARPIC website. Is that true, Andrew? People
Yes,
access them
I
later?
don't think. Yeah, I think we just got access to like the last few right before, so we will work on getting those immediately after. So I'm sorry if I have to cut people off today, but the rest of the slides will be available after the session.
Great. Okay, and our next speaker is Chris Cox from NOAA.
Thanks, Ellie. Hello, everyone. Can you hear me okay? Great, great. Chris Cox from NOAA PSL. One of NOAA's Arctic priorities is advanced sea ice forecasting capabilities. And one of the primary tools is fully coupled ocean ice atmosphere models. And thermodynamically, these models are effectively forecasting the ice column's energy budget. And consequently, observations of the surface energy budget are really valuable for support for the modeling. But these measurements are pretty rare over the sea ice. Our lab, PSL, and the Cooperative Institute series, leveraging with NOAA and NSF, developed the Atmospheric Surface Flux Station, or ASFS, which is shown in the picture, to make the needed observations. The ASFS measures the full radiation budget. It's equipped with sonic anemometer and gas analyzer for deriving turbulent heat fluxes by eddy covariance. It has conductive heat flux plates, meteorology, and a number of other things as well. During the Mosaic expedition in 2019 and 2020, we successfully collected more than 650 days of data using 3 prototype stations in the Central Arctic Ocean. So that was a really successful start to the program. The ASFS at Mosaic, we're on a sled. You can see it in the photo. It's already formed sea ice that you put this on. So it used about 65 watts. It could be on its own for about 2 months. And a major success was careful instrument selection and power use tuning that was well tuned for the Arctic environment. The instrumentation was really kept ice-free almost continuously throughout the expedition. But the next step is to turn these into proper buoys. We're currently leveraging with a multi-year technology development project led by ONR and APLUW that is building large new high-power buoys for ONR's AMOS project, the Arctic Mobile Observing System. So we adapted ASFS for that, reduced the power, and 2 experimental buoys were deployed this past week in the northern Beaufort from the Sikuliak. I'd hope to be able to show you a photo of that, but unfortunately the deployment was just really recent and they haven't cleared the photos for sharing yet. But I do want to emphasize to conclude that this present work is really experimental, and hopefully it will be successful with several sequential iterations over the next few years. But and ultimately, if successful, the project could be able to support full ocean ice atmosphere energy budget measurements year-round in the Western Arctic. Thank you.
Great, thank you, Chris. It's really impressive they didn't ice up much in Mosaic. It was definitely challenging conditions. Our next speaker is Tristan Lecuyer from University of Wisconsin-Madison.
All right, thank you. Well, on the topic of experimental measurements and Earth, the energy budget, I'm going to talk a little bit about some new experimental measurements of the polar regions from satellites. And I have a lot of information on these slides, but I also have some notes at the bottom. So I'm intending people to look at these afterward. I'm going to go very quickly through it. The main point here on this slide is kind of the motivation for this polar radiant energy in the far infrared experiment. And that is this graphic just shows the 2 energy budgets of the Arctic and Antarctica. And the main point, as we all know, is that the Arctic and Antarctica are cool regions because they emit more long wave radiation than they take in the visible. But if you look at the various sources of downwelling and upwelling long wave fluxes in the Arctic, you'll notice that no matter whether you use weather models like reanalyses, climate models, or observations, the uncertainties remain very large. And one of the reasons for that is that we only measure a fraction of the Planck function at the temperatures of the Arctic and Antarctica, as I'll show on the next slide. And so PREFIRE is actually hoping to reduce uncertainties in these polar thermal fluxes and the processes that influence them, but on the scale of the entire Arctic. You can go on to the next slide. Oh.
I only have one slide for you. I'm sorry. I can check real quick to see if I have it on a tab.
Okay, well, I can keep talking anyway. So the idea, as I said, is that PREFIRE is going to measure far infrared radiation. It's radiation at wavelengths longer than 15 microns that is not currently, there it is. Yeah, so if you look at a typical Planck function here, you see that grayed out area is all of the energy at longer wavelengths that's not currently measured by satellite. You can click one more time, actually 2 more times if you want. I got a couple of animations. There you go. And so PREFIRE is going to actually measure radiation out to 54 microns, filling in this gap in far infrared radiation, and hopefully filling out and improving our knowledge of thermal flux exchanges, heat exchanges in the polar regions. But also these longer wavelengths carry information about low levels of moisture, cloud cover, cloud microphysical properties, and surface properties that we're going to try to infer across the whole Arctic. And if you go to the last slide, this is again one that you can take your time. Oh, there you go. Take your time looking at this. This basically outlines the whole mission, including our science. And I'll just highlight the couple of facts in the center here that's interesting. So again, we're measuring far infrared radiation for the first time. We're using 2 different CubeSats, and as they intersect in their orbits, we'll be able to actually look at differences between their measurements to get at processes going on in the Arctic. And we're using CubeSat technology. So this is where the new technology and experimental technology comes in. The satellites themselves weigh about 10 kilograms in total, and the instrument only 3 kilograms. So it'll be novel to try to get science data from these small CubeSats. And also, we're hoping to connect directly to the modeling community and improve Arctic climate predictions by trying to interface these measurements with things like climate models. And we have people who are working on cryosphere models and also global climate models directly on our team.
Great, thank you, Tristan. Our next speaker is Ken Cooper from NASA JPL.
Hi, thank you. I'm Ken Cooper from JPL. We'll be discussing our advanced radar systems above 100 gigahertz for Earth science remote sensing. Maybe you can go to full screen mode for people, but if not, I'll just talk through it. So Earth observing radar systems traditionally operate up to about 94 gigahertz, which is a millimeter wave band. And beyond that, there's what's called a terahertz technology gap between the microwave domain and the infrared and optical domain. And new technology is emerging, partly with 5G and so forth, to bridge that gap. And JPL is at the forefront of that. As an example, in that top middle, there's a device where we can achieve world record power in a solid state device at about 170 gigahertz. In radar systems, what this lets you do is, first of all, we have sensitivity to important water vapor resonances. And second of all, we can detect small particles. So in the lower left, it describes the VIPR radar system that we at JPL have developed. VIPR takes advantage of the water absorption resonance at 183 gigahertz water vapor in order to measure water vapor inside of clouds. This is a very difficult measurement to make otherwise, and it's important for modeling the climate and doing weather forecasting. So the bottom left shows some nice cloud pictures we can obtain with VIPR, and the bottom right shows humidity profiles, which are really the key ingredient for understanding thermodynamics of clouds. So VIPR is shown in the center, and we're about to fly on NASA P3 aircraft very soon. In addition, we're exploring radar systems up at even higher frequencies. At 240 gigahertz, there's an instrument called Cloud Cube my colleagues are working on. All this is supported by the NASA Earth Science Office. Cloud Cube is to measure clouds at very high frequencies where the wavelengths interact with small hydrometers particles. And finally, we're even going up to 560 gigahertz with a Wasser instrument to potentially measure humidity on Mars, and also 360 gigahertz for measuring sublimation inside blowing snow. So these are some of the things that you can do with very high frequency radar systems.
Great, thank you, Ken.
You're welcome.
Our next speaker is Shel Ginteman from the Farallon Institute. I probably said that completely incorrectly.
Sally, you got all the things that people mispronounce right, wrong, right. You got my name right, and then the Farallon Institute wrong, but that's fine. So I pictured in the center is a Saildrone surface vehicle. It captures observations at the air-sea interface using autonomous technology. They're basically robots of the sea. These vehicles combine wind-powered movement. You can see it's a solid sail on top. With solar-powered sensors, you can see the solar panels along that sail and that wing and along the top of the Saildrone vehicle that power sensors. And these missions can last up to a year. The near real-time data and vehicle control is through Iridium satellite link. So we're seeing data as it comes in. We're pushing to the GTS for weather. And we're also controlling the vehicle via that Iridium satellite link. So to give you an idea for size, the vehicle's hull is 7 meters. The hard wing is 5 meters tall. And the keel is about 2.5 meters draft. It weighs 750 kilograms. They move about 1.125 meters per second, so about 100 kilometers per day, which of course depends on the wind. Both NASA and NOAA have collaborated to run Arctic missions since 2019, and the Arctic air-sea interactions are critical to understanding Arctic amplification, to understand how modeling and how the changing sea ice and ocean impacts our lower latitude weather. Right now, there is no satellite that measures the air-sea exchange of heat and moisture fluxes. So these Saildrone observations are really critical. The cost to deploy in remote regions includes shipping to a major port. A team flies in, essentially puts it together, pushes it off. They do a couple days of tests, and then that team goes on to deploy them somewhere, another set of Saildrones someplace else. So it's actually reasonably inexpensive to deploy these in the Arctic, and they've been there for several years now. They've circumnavigated Antarctica, and they've been deployed in every major ocean. Next slide. Okay, so in 2019, here's some results. This is showing you we got a little bit too close to the sea ice. As you can tell, we got stuck a little bit. And it shows you just some of the data that's coming back. And this is what I see in the platform that I look at when I control the vehicle. And if you click, so there's where we went in 2019. There were a number of vehicles, but it was a joint NASA-NOAA cruise. And this is showing the ocean temperature as we deployed from Dutch Harbor and then went up into the Arctic. Next.
And if you can summarize very quickly too.
So click, and then, so these are, we also strapped some thermistors along the keel, and this is showing you 5 degrees of warming in just the upper 2 meters of the ocean, which is a really intense amount of warming that lasted over 2 days in the Arctic. So those are the temperatures of the ocean going up by 5 degrees in the top 2 meters of the ocean. Thank you.
Great, thank you. And our last speaker is Kevin Kossel from NIST.
All right, thanks. Going to talk a little bit different topic now. It's a system that hasn't been deployed to the Arctic, but it's a sort of new spectroscopy system that we're developing at NIST. So kind of try to highlight some of what we've done to kind of get people thinking about possible measurements that could be done elsewhere. So looking for kind of collaborations or, ways to deploy this. So the idea is called dual comb spectroscopy. Basically, it gives you this broad spectrum, but with a really high spectral resolution, so much higher than OpenPath FTIR, and no instrument line shape, so high accuracy measurements. Kind of get PPB level trace gas sensitivities over these long open air paths. So we send the light out over hundreds of meters to 5, 10 plus kilometers out to a reflector and back. With the long open paths, we can measure both trace gas sort of concentrations, but also emissions from point in area sources. And so that's kind of the main focus of some of what we've been doing. So we have a near infrared system that measures greenhouse gases and ammonia. We've used that in oil and gas fields to look at emissions from oil operations, for looking at greenhouse gas emissions from city scales. We can mount this reflector on a drone, so we can do spatial scanning, so get emissions by doing vertical sort of flux plane scans or horizontal scans to look at concentration gradients. And then an example of how it was measured emissions from a small feedlot by having paths both up and downwind of the feedlot, so a distributed source, looking at emissions from that. So that's a very robust system. We have a new generation system in the mid-infrared that can detect methane, ethane, propane, some other VOCs, formaldehyde, N2O, CO, and ozone, looking at other things as well. this is an example of deploying that to a oil and gas drilling operation where we have a beam path on two different sides coming from one system down in that van in the corner. And now you can look at enhancements of gases on one beam path versus the other to look at emissions from the site of interest. And so
and Kevin, if you could wrap up.
Yep. The plot on the bottom just shows methane and then some VOC ratios all increasing at the same time. And that's all I have.
Great, thank you. Thanks to all of our speakers for staying on time. I know 2 minutes is very short when you're describing your research. So we do have a couple of questions in the chat. Maybe we'll start with, there's one to Shell. Chris, do you want to ask that?
Sorry, yeah, I was just actually answering someone else's question. Yeah, Shell, just before you tuned out, you said you had measured a 5C increase in temperature, and I was just curious if that was sampling spatial variability, or if you think that you actually saw the ocean warm that much.
We think it was actually more than that. So the temperature difference that I showed was relative to the bottom Seabird 56 that we had at the bottom of the keel, and the gradient was still fairly strong, even with the one that we had just above that, but we only had that as our bottom temperature. So those other temperatures were relative to that temperature, and we believe that bottom temperature was still warming from the subsurface temperature. So we think that's the minimum amount of warming that we saw, and we believe it was related to extreme atmospheric heating and clear skies, so solar heating. So it was not sampling because there was very low wind, so we weren't moving. It wasn't like it went over a warm, very shallow warm current. It was that the surface of the ocean was being heated by atmosphere and solar.
Thanks, Shell. That's pretty interesting.
Great,
Yeah.
Thanks. And Chris, do you want to go ahead and orally answer the question you had in the chat?
Sure. I was answering Heilong's question. Does the ASFS perform direct measurements on the surface turbulent fluxes? Yes, we have a sonic anemometer and like our gas analyzer, we collect 20 hertz samples. And I mean, for Mosaic, we're archiving 20 hertz samples, like 120 megabytes a day. So yeah, you can derive turbulent heat fluxes any way you want through eddy covariance there. But obviously the data transfer limitations for a long-term autonomous station mean that we would have to do the processing on board. It would still be eddy covariance, but we'd be transmitting the fluxes.
Great, thank you. Tristan, do you want to go ahead and ask your question?
Sure. One of the points that I actually forgot to mention, but PREFIRE is scheduled to launch in spring of 2023. And so seeing the ASFS and Saildrone talks, I was just wondering, Chris and Shell, do you have a plan for, or I guess, are you funded to continue making those measurements and doing that development through into 2023? Because the flux measurements in particular, as well as maybe the surface temperature, would be really good validation data for PREFIRE.
Yeah, Tristan, I saw your PREFIRE is so complimentary. Right now we have funding for 2022, only for one vehicle though. After that, we don't have any funding. It's been a 5-year project, so it's the end of a 5-year project. We can certainly work. NOAA often has vehicles up there, so we should talk.
Yeah, that'd be great.
And yeah, I mean, the funding on the ASFS side is sort of in flux, but I expect there probably will be more measurements of this sort developing over time. And we also have had some conversations with PMEL, Qidong Zhang, for instance, and their so NOAA's Saildrone work, and we've discussed the possibility of doing some complementary studies at some point. Like near the ice edge, for instance, with the buoys.
Great, nice to see some potential connections coming out of this meeting. Let's see, I think there was a question I missed earlier in the chat from Jack. Jack, do you want to come off mute and say that, or I can read it?
Well, I was just asking Kevin if he had thought about sending his instrument or some version of it up to Arctic regions to kind of look at this whole notion about all of the carbon coming out of the thawing permafrost, which has come in from a lot of really small scale studies, but like the top down people keep saying they can't see it. And a long path, I think you said several kilometers, maybe up to 5, might be a really good test of that, of the magnitude of any really enhanced flux of methane and CO2 out of the tundra or other thawing permafrost.
Yeah, I think that's a great idea. We've sort of thought about it briefly, but don't really have any good connections, I would say, for sort of where exactly to deploy or what the configuration would look like exactly. I think we could definitely see something, so it'd be a question of where and how exactly.
Well, I don't know. You might think about. I mean, it's almost too late for the NASA Above program, but I think the DOE, what's it, Next Gen is still ongoing. I mean, so they've done a lot of really small scale stuff that sort of is interested in this issue.
That's a great idea. Thanks.
And Hailong, you had a question?
Yes, I have a question for Naruki about, since he didn't have time to talk more about the model, observation model closure study. Could you please briefly just describe your plan on how to perform that?
Sure, thanks for asking, Hailong. So I'm collaborating with 2 modelers, Shahon Liu and Susanna Barros, Shahon from Texas A&M and Susanna from PNNL. The plan is with Shahon, we're going to be doing the Arctic INT modeling closure with E3SM MAM, I believe. It's 1 degree by 1 degree resolved model with 72 vertical levels, I believe. And we're going to be using MERRA2 meteorological data and a few other specs I have to check with Shahon. I think the similar configuration will be used with Susanna, but I think the novel aspect of measurement closure studies for ice nucleating particles, we're going to be specifically looking at the influence of high latitude dust. We think, yeah, I mean, including the high latitude dust in global models for the atmospheric ice nucleating particle aspect would be important, and we'll just see what we can find.
Okay, great. Yeah, I was just wondering, are you going to perform the whole global modeling or single column modeling? But the local sources and long range transports are both very important. Thank you.
Yes, thank you. Yeah, we are going to start with a single column model, of course, like easier first. But our expectation or the ambitions would be scaling up to the global scale in few years. Okay.
Okay, great. Thank you very much.
Are there any other questions? I had one for Ken. So the VIPR in-cloud radar, you said that was going to be deployed on an aircraft soon. What campaign is that, or where is it going to be deploying? Yep. We might have lost Ken. I'll put that in the chat for him later. Any other questions from the audience? I know you always have a question, Will. You're being really quiet.
Yeah, actually, I do.
I knew it.
I guess the question is, so these are all really, I mean, some of these are technologies we've seen deployed for a few years, like the Saildrone. Some of them are a little bit newer. We talked about the funding for the Saildrone project, maybe running out in a year. So I guess the question is sort of broader. What do each of you, and you can each address this briefly, what do each of you think the potential is for expanding from what are fairly small scale studies, in some cases done by individual labs, up to larger studies, even Pan-Arctic, to get some of the comparisons that we need to look at some larger scale processes. So we got some great technology here. What's the next step, and do you see a pathway to expanding the spatial data collection? So you can just all take it. Why don't you take it in order from which you spoke, if you can even remember that, because I don't.
I think Naruki was first, but I'm not sure any of them are. They all seem a bit hesitant to take on your question. Well, go for it, Naruki.
Oh, yeah. So I'll be brief. So yeah, I mean, I think, well, my technology is the new technology to measure INP. It's brand new. Yeah, it just came out. It became like commercially available, but it has really, really reliable, measurement capabilities. And what I'm hoping in the next 5-10 years would be deploying more pine chamber in other Arctic locations, stations. That way, yeah, I can say a few things about spatial, the temporal distributions of INPs. So my ambitions, deploying more chambers. Thank you.
With respect to the surface flux stations, there are aspirations within ONR and APL for there to be potentially a large array of these sorts of things.
I'll mention about VIPR.
Running with each with a lifetime of.
I'm sorry.
Go ahead. Yeah, go ahead.
Sorry, you broke up a bit there, Chris. I'm not sure we heard the end of your comment.
Oh, sorry. I was just saying there are aspirations within APL and ONR to have a pretty large array of these buoys at some point, but that's a ways down the road.
Yeah. Okay, Ken?
I'll mention for VIPR, our current support is for airborne tests on a program called Impacts, where we'll be piggybacking to study winter storms on the East Coast. But we hope to expand our airborne campaigns, in follow-on years if we find support for that, including the Arctic, including for our 240 gigahertz cloud radar. But as a JPL employee, there's a real big push to get this to space and with NASA. And so we're looking at the kind of 2030s timeframe as having a potential differential absorption radar system in space for a global coverage of inside cloud humidity.
I guess I can comment on the question from the satellite perspective. I think it's actually good to piggyback right on that point. I have this, I guess it's somewhat, I don't know, maybe long-term goal. And I think a lot of people on the call, and maybe this is part of the reason for IARPIC to begin with, is, to try to somehow use the satellite to expand the scope of ground-based measurements. And I think it kind of goes along with the last comment, that if we can, I think there's a sort of a systematic approach of going from more of the local scale measurements to airborne measurements that can cover a larger domain, to satellites that can kind of routinely monitor, and not just one pole, but both poles. And so I think, I don't know, I guess one of the things that I think this group is still sort of working on is how better to coordinate those ground-based airborne and satellite assets to try to bridge the gap that apparently exists still between them. And we tend to use ground-based observations to validate the satellites, and that's about it. But I don't think we have a comprehensive plan yet still for making detailed measurements in locations, and then expanding them to larger regions using aircraft, and then expanding them to the entire region using satellites. So I would still like to continue that conversation and see how we can kind of create a plan for doing that. I know different agencies are involved, and I think that's why this group would be kind of an ideal group to talk about that. Anyway, that's my thought on it, but that's where I envision PREFIRE is hopefully expanding the scope of the ground-based observations to cover the entire region.
Great, thank you. Anyone else want to comment on Will's question? Nope.
I
Yeah,
want
go
to
ahead,
jump
Phil.
in real quick. I don't know if I'm out of order or not, but Saildrone through private funding has gathered about 190 million in startup funding. No, exactly. I see your eyebrows raising, Will. So, and Tristan, you know the EVI and the EVM budgets. I mean, this is an entire EVM mission for something that is a really cool instrument. But let's be clear, it was started by people who were doing land with, they had a hammer and they were looking for a nail. And there's a possibility, I think, of like a multi-agency private-public partnership to study the Arctic here. I mean, I'm based in San Francisco, so I hear a lot about these things, that Saildrone funding. Also, there's this thing to cover the Arctic with ice globules, and there's all sorts of startup and funding going towards the Arctic because it is the canary in the coal mine. And I think the selection of PREFIRE by NASA had a lot to do with the attention that the Arctic is getting for our climate crisis. And the fact that we still don't have a really solid understanding of, what are the energy balances in that area and how do they affect lower latitude weather is we have a compelling story to build a big in situ field campaign that can support this leap from in situ field campaigns to atmosphere to satellite processes in 2023, 2024. And I'd love to see this group with like all of the different people involved in this start to build that story and maybe go for a big campaign event that we can start to raise funding from both private and public entities. And yeah, I'm really jealous over the 190 million they raised. I mean, I have ideas too.
Yeah, that's a good amount of money.
Yeah, I'm not even sure I'm not sure what that means. I'm not sure it's good, but I mean, it's encouraging, but yeah.
Yeah, I mean, it's a different topic of conversation for it's a totally different model of instrument development than coming from academia. It's coming from startup funding, but that doesn't mean that we can't use it. I mean, that's basically why I've said, well, they're going to pay for it. I can do science with this, but that we can take it, we can look at what they're doing and maybe learn from it as a science community.
Okay, we have just a couple more minutes. Frank, I see you turned your camera on. Did you want to say something?
I just say that maybe something to pursue is if they do create the new NSF Directorate for Technology, Innovation, and Partnership, that might be a place to go to try to shop that concept around. We'll see what happens.
That's an interesting thought. Yeah. I think many of us, well, I'm sure you, but many of us are also interested to see what that technology division will actually look like and what it will do. So yeah. Okay, any other questions or comments?
I'd like to just thank all the presenters, and this is for the couple of you who haven't been on ARPA before. This is a perfect example of why ARPA is so valuable, because we obviously made some connections here. I didn't catch all of them. That might or might not have been possible in other venues. So this is really one of the things we like to see come out of IARPIC, and it doesn't always manifest itself quite so quickly in the same meeting. But we'd certainly like to follow up and encourage you all to follow up on all those connections. So thanks for your time.
Sandy, did you have a question or a comment?
Yeah, I guess it would be a question if there's time. I know there's also a need to do a little bit of a wrap up, but in these cases, I think how the science met the technology can be kind of an interesting story. I think Shell indicated that in the case of Saildrone, it was the technology coming to look for the science. It sounds like that might have been the case the ice particle nucleation. You said the technology became available and then I used it. But I think in the case of what Chris Cox described and some of the others, and PREFIRE is probably a case of this also, the scientists pushed the technology in the direction where they saw the gap. And I think that's an interesting thing to track, because what are we doing to support or foster or influence that meetup, so that, you know, people like Chris Cox don't have, or Thijs de Boer don't have to spend half of their science career developing technology. And then on the other hand, you don't end up with something like Saildrone, where it's like the hammer looking for the nail. And so, to Frank's point, you know, I think this is an interesting interface to examine. And if any of the speakers want to speak to what they see as the kind of optimal story for this to happen, I'd be curious to hear that.
Well, I'll just mention really quick, you know, in the context of the work we do at JPL, one of the nice things about our institution is that we have scientists and technologists here co-located, and we work very closely with each other and try to have the scientists guide us on what technologies to develop. But I do understand technologists who come up with something and then look for a good application for it.
I think it's a really interesting question, Sandy, and maybe something we can pursue, thinking about a bit more in the future, the best ways to bring scientists and technologists together.
I think that's really key, Sandy, is like JPL, like I work a lot with JPL, and Tristan, I'm curious to hear your experience, but it's coming to technologists with these gaps and then trying to see if they have a solution that might work to fill those gaps. And then the reverse is true, which it's technologists coming and saying, I have these capabilities. You know, it's a partnership, really. So whether it's being forced, you know, like Saildrone was a little bit more on the hammer looking for a nail, but you could say that of most technology, it's this generating science and technologists to work together and understand where these can be matched. It's, you know, it's like match.com for scientists, I guess. But it's hard, and it requires sort of a unique skill set, I think, but having these opportunities to generate ideas that like happen at JPL, but how do we move that outside of JPL and more into things like AGU or other opportunities?
So I'm going to let Tristan comment, and then I think we're going to have to close. So quick comment.
Yeah,
Tristan.
just one. I mean, the quick comment here is, and so obviously PREFIRE is a joint venture between JPL and University of Wisconsin, so I work closely with JPL as well. It does help to have the technology. In fact, I think you almost have to have some aspect of the technology already ready to go before you can apply the science problem. So in our case, there were a couple of planetary science, a moon mineral mapper and a Mars diviner mission that had already developed some of the technologies. And what PREFIRE did was came along and said, okay, we have this specific application, we need it miniaturized for CubeSats, et cetera. And so that's where the collaboration began and worked. But we did have some technology, and then we had a scientific need, and we kind of then brought them together and then advanced it. So anyway, that's it.
Yeah, great, thank you. Andrew, do you have any updates or close out information?
None other than that this meeting recording will be uploaded on the RPIC webpage, and I've uploaded all slides. So even though I had to cut a few people short, those are all available.
All right, great. Thank you. Well, thank you very much to all of our speakers. I think this was a really great meeting, really great discussion at the end. And we'll take some of these discussion points back and maybe come up with some future meetings and future discussion around them. So thank you all.